Welcome back to the part 2 of lecture 10. We have been talking about electrical properties, and this table I showed you in the part 1. This is very important for you to know that metals have a high conductivity compared to semiconductors and insulators. So, by now you must know what values are required for metals to become conductive, what values are required for insulators and ceramics and semiconductors. Well, you can also do a simple problem. This is for you to do some homework. What is the minimum diameter of wire so that voltage drop is less than 1.5 volts? Let us take a CU wire, and you can do that. This problem is solved here. Resistance is given as what? Resistance is given L by A sigma, and for copper you know the conductivity already 6.07 10 to the power 7, and A is where which is given by pi d square by 4, and V is what? V is 1.5 volts, and you have to also mention here I is equal to 2.5 amps. Then only you can solve this problem. So, you know the length L is also given as 100 meter. So, what you need to do is L is known, okay, V is known, I is known, sigma is known, A has to be found out, and A is equal to pi d square by 4. So, you can easily find out that. Plug in all these values, you can get an answer. That is the minimum diameter required. This is important for copper wires, right, because diameter of copper wire changes for different applications. So, that is why this is important, and you know you will get the answer 1.87 millimeter. So, if I want to put things together again, that is a problem actually. If I want to put together all these metal semiconductor insulators in terms of resistivity, they look like this. So, silver, gold, copper, aluminum, they have resistivity in the minus 9 ohm centimeter. Resistivity has to be ohm centimeter because conductivity is 1 centimeter inverse. So, bismuth or germanium, they have a resistivity 10 to the minus 5, 10 to the minus 3. Silicon has a resistivity 10 to the minus 10 to the plus 3. Remember, these are room temperature resistivities. Window glasses, very high resistivity 10 to the power 5. Silicon dioxide, pure silicon dioxide is basically a sand, right, pure but without any impurity, 10 to the power 17. That must be a good insulator. Polymers will have the same value, 10 to the power 15, 10 to the power 14 ohm centimeter. So, to give examples of that, colorful pictures, copper, gold, silver, they are conductors, they shine. Semiconductors, they do not shine at all, they look like black. Silicon is like a black color. Gallium arsenide also look like a gray. Glass is insulator, it is transparent. Alumina, it is also translucent, it is white, remember that. So, therefore, color of the object also can tell you something, whether it conducts electricity or not. So, copper is the most important, it is very ductile, soft, metallic, it can be easily made, I told you, that is why it is widely used as a wire for electrical conduction. Semiconductor like silicon is a hard and brittle. Silicon is very brittle, if you just throw it off it will break into pieces. So, therefore, silicon is bonding is covalent. Normally bonds are mixed, but predominantly it is covalent. Copper is metallic. This bonding actually is very important because we are going to talk about it, how this bonding is going to give us the answer why copper is so highly conductive. And then you have insulating like diamond, diamond is insulator. It has a covalent bonds. Some of the covalent bonding materials have also have, insulator also have ionic bonds like sodium chloride. This is an ionic bonded solid which does not conduct electricity. So, now you must be understanding why metals conduct electricity, because there is a lot of free electron and metallic bonds have free electron bonds. So, electrons are the ones which do this job, and they are the elementary particles. Their importance in our life goes much beyond the present day discussions on the role in electronics, optical, magnetic properties of material. There are many other particles other than electrons like leptons, mesons, bryons, bosons. Let us not go into all these things, just to show you that electrons are also important elementary particle which contributes to this electrical properties. So, to understand electrical properties of material, we need to understand interaction of the electrons with the material containing those electrons. But we will focus mostly on crystalline materials. Well, let us not talk about much of glasses and other things. So, we will talk in terms of two important models. One is a classical model which is called Drude model, and another one is a quantum mechanical model which is nothing but a Kronig-Penney model, and then we show about band diagrams later on. So, classical model is Drude model which is depends on the classical treatment. Quantum mechanics, I hope you have some idea of quantum mechanics, but if you do not have, I will explain or give you some reference of books which you can read into also. So, electrons are discovered long back 1897, more than almost how many 125 years ago, and it was discovered by J. Thomson. This is an old picture of Professor J. Thomson, and remember that he discovered using such a kind of a device known as cathode ray tube. That is a tube in which you can produce glow up electrons cannot produce. That is what has been done. This is taken from American Institute of Physics, as you see, and you can read a lot about this website. So, J. Thomson is a very famous professor. He discovered electrons, and his students discovered proton and neutron. So, what is the classical model? It says at the turn of 20th century, after discovery of electrons in 1897 by J. Thomson, equipped with the knowledge of kinetic theory of gases, Drude applied a simple idea embodied in kinetic theory to explain the conduction in electrons. This is the, in a nutshell, classical free electron model. So, Drude applied kinetic theory of gases given by Maxwell, knowing the electrons are the elementary particles. So, in metals, when atoms of elements that exist in the metallic form come together to form a solid, there will be valence electrons from each of the atoms, and they will be completely free to move around, and these electrons form a sea of electrons, what is known as a conduction electrons, and they move around the positive charged part of the atom. So, that is what is the, in a nutshell, this Drude model. It talks about the electrons which are free to move around this positively charged. So, if I have positively charged nucleus, and these electrons can move around like a cloud anywhere, and that gives the conduction. So, Drude treated the sea of electrons as electron gas, and then he applied, as told to you, kinetic theory of gases to explain the behavior, but he the positive ions are assumed to be immobile. That is okay. For contrast, density of typical monoatomic gas at room temperature is what? 10 to the minus density of electrons actually in the monoatomic gases like helium, neon is at 10 to the 19 centimeters minus cube, while in metals density of electron is 10 to the 20 per centimeter cube, which is almost 1000 times higher than the any monoatomic gas at room temperature. So, in spite of all these things, kinetic theory of gases was used for electrons in metals. Well, we will not talk how it is used, but I am just giving you important information. So, now these electrons are free, they are free to move around the atoms. So, they will then collide each other, they collide with the positive ion also. So, there will be independent electron interaction between collisions, and also there is possible to have electron ion interaction, but Drude assume there is no electron ion interactions, electron ion collisions are not present. It is only, he also assumed no electron interactions. Remember this. These are the two important. So, between the collisions, obviously electrons are colliding, between the collisions there is no electron interactions and there is no electron ion interactions. At the collisions are instantaneous, it happens immediately, and that abruptly change the velocity of electrons. Collision between the mobile electrons and immobile ions only, no electron collisions happens. That means collisions happens only with electron and the immobile ions. That is what it is. So, when there is no potential applied, electric field applied, electrons are moving, free electrons moving, they collide with these positive charge ions, immobile ions, and then move. And therefore, once they collide, the velocity changes. Velocity changes means value and magnitude as well as direction both changes. And this is what you will get in Wikipedia, sometimes useful. This is a schematic picture from Wikipedia when no electric field is applied. So, electrons will keep on hitting the ionic cores and may not reach the other end of the solid, that is why they do not conduct. But if you apply a field, the electrons will move. So, there are few assumptions. So, the assumption is that there is no reason why does the collision was happening. Collision can happen because of temperature also, but no reason given. No explanation is given how does collision takes place. Only effect of collisions or scattering in the terms of free parameters are used as sufficient. So, two important things was used. One is the relaxation time, that is the average time between the collision, two successive collisions. It is taken to be independent of electron positions and the velocity. Electron also achieve thermal equilibrium with their surrounding through this collision. That is, velocity of electron just after the collision is determined by the surrounding temperatures and is in random directions. It is no way related to the velocity before the collisions. So, this is what was used by Drude. So, when there is no electric field, electrons will follow parabolic path, hit, you see electron has hit this at ionic core, then move like hit another and hitting finally reaches here. So, if you apply electric field, it will be much easier. It can go through this. This is taken from a lecture available in Harvard universities. So, by Professor Jones, you can also go through it. So, now we can always write down Ohm's law like this: current density is equal to sigma conductivity multiplied by the field. So, this is the field, this is conductivity, this is your current density. Current density means current passed per unit area, and we can always explain this in terms of a circuit. You can see here there is a battery and you have a connected a wire of length L and cross sectional area R, and if you just put a voltmeter, you will see there is a voltage drop because of this presence of this conductor. If this is not there, then you can always measure using the current using ammeter. So, this current is what is going to give you the voltage drop equal to I into R relationship. Okay. So, this is what is used to test this is correct or not. So, now as we have discussed that the way it happens is the electrons are basically moving, in the process of moving they collide in the ion cores, and finally after each collision the velocity is changing and finally it reaches to the other side of the sample. That is why this conduction happens. So, important parameters is what drift velocity, velocity at which it is drifting. This velocity represents the average electron velocity in the directions of the force imposed by the applied field, and it is directly proportional to the field. If you apply electric field, the velocity at which electrons are drifting, electrons are moving, that will be related with the field, and the drift velocity is given as a mu e multiplied by field, and mu e is your mobility. This is called a mobility parameter, remember. These fundamental equations are important for you to model when you do machine learning. So, whatever happens during collisions different paths, finally there will be net electron motion, and this net electron motion is what is important. That is what gives you the conduction. So, net electron motion is happening because of the field, applied field. It will also happen if you do not apply field, but it will happen very less, scarcely. So, the three fundamental relationship I can give: one is the drift velocity, which is equal to mobility multiplied by electric field, then a current density that is equal to conductivity into electric field, and whatever conductivity, conductivity is obviously number of electrons into charge of electrons into your mobility. So, this we written what? This is nothing but N E V D by epsilon by E, electric field. So, we can always put down this N E V D by, that is what it is, because epsilon this field will get cancelled. So, that is what is your current density. So, you can clearly see current is related to the number of electrons multiplied by electronic charge and multiplied by V d, the drift velocity. That is how it is calculated. So, these three equations are related, but they will be all used for modeling purposes. But Drude model as such is good, but it is not free of any defects. So, there are a lot of observations which could not be explained by Drude model. First one is conductivity. It suggests that higher the valency, higher the conductivity, right. Number of electron n is there, right, you can clearly see n is there. So, higher the valency, higher is the conductivity, but best metals have only 1 or 2 valence electrons. There are other metals has more electrons, but the conductivity does not change. Second one, which is cannot explain, is the Hall effect. Hall effect allows you to determine the sign of change charge carriers, whether it is a electron or something else. But in contrast to assumptions of Drude theory, some metals show Hall current like beryllium, magnesium, aluminum, indicating positive charge. So, that means there are other species which can carry charge, because it was not known actually in those days that the Hall also can carry charge. It came only when semiconductor discovered. So, absolute size of the charge determined by these measurements of the Hall current disagrees in many cases for metals, and this is mainly because the assumption that integral number of valence electrons being responsible for the charge transport. It can have non-integral number also people have observed, that is why it cannot explain. It can also cannot explain thermal conductivity, specific heats and many other things. So, therefore, Drude model is good for many explanation, not for all. That is why we talked about quantum mechanical model. Quantum mechanics came at the beginning of the last century, something around 1901, and that is why quantum mechanics can explain things very easily. But let me talk about a little bit of quantum mechanics, because many of you may not know. So, device physics is basically based on quantum mechanics, and it connects between electromagnetics as well as statistical thermodynamics. Almost all the solid state physics concept rests on these 3 pillars of modern physics: quantum mechanics, electromagnetics and statistical thermodynamics. So, important aspect is to know is the particle wave duality. Particle can exhibit wave like behavior, that it can produce interference patterns and can tunnel through potential barriers, like electron can tunnel through potential barriers. Electron can also give interference patterns. How it is possible? That is why de Broglie first time hypothesized a wave particle duality by this fundamental equation, which is nothing but lambda equal to h by rho, so h by p, and where this is h is the Planck constant and p is the momentum. So, wavelength is equal to h by mv and momentum as a component mass, right. That is why particle wave duality was explained, and electron is basically can behave like wave. We know electron undergoes diffraction. This is the electron diffraction pattern, and see on your screen here. This electron diffraction pattern, that is only possible because it produces interference, and interference leads to diffraction. So, therefore, electrons actually show both particle and wave behavior, and this can be explained using this de Broglie's equation, the hypothesis. So, particles can exhibit features like it can produce interference patterns, a tunnel through, but electrons waves can show diffraction like X-ray diffractions, electron diffractions. So, this is only can be explained using de Broglie hypothesis. So, fundamental aspects of fundamental aspects of quantum mechanics is basically given by Schrodinger equation, and this is energy equation basically. You see, energy is equal to total energy is equal to kinetic energy plus potential energy, any system, and kinetic energy is given by P by m twice m. You must understand why. Kinetic energy is equal to half m v square. So, I can write down m square v square by 2 m. So, m v is basically p square by 2 m, that is why it comes. So, therefore, E is equal to p square by 2 m plus V x. So, we can always write down this whole thing in terms of wave mechanics. So, E psi is equal to p square by twice m psi V x psi. Psi is nothing but a wave, electron wave. So, now you understand very easily, right. The energy and Schrodinger equations are related nicely. So, every classical variable in physical quantity in classical domain it becomes nothing but an algebraic operator in quantum mechanics, like this one h square h cross by twice m d psi d2 psi dx2 plus vx psi is equal to E psi is also an operator. So, you can say this is equal to your E psi, this part of the equation, this is equal to second part of the equation, and this one is explained is converted into that. So, we can always do that, we can convert this, and once you solve this equation you get everything, you get electrons, you get where the electron lies, but problem is solving the equation. That is where the real challenge lies. It is not easy to solve, but there are some other parameters which you also know. So, this function, wave function psi x is very important. That tells you where the electron lies, and this is obtained by probability density function, which is nothing but psi x multiplied by psi star x, and this is psi star x is exactly opposite of psi x in complex algebra. It is complex conjugate actually. Psi x and psi star x are complex conjugates. If you multiply that, you get that. And once you have p x, if you multiply over the minus infinity to plus infinity, if you integrate, you get the distribution of electrons that must be equal to 1. So, probability density can also allows us to calculate expectation values of any physical quantity. That f x p is basically expectation value, that is integral minus infinity plus infinity psi x f x and psi star x dx. This f x is basically nothing but a expectation value. So, therefore, all these parameters can be calculated once you know this wave function psi x. That is important. That can be obtained from the solving these Schrodinger equations. Well, free electron model can modify this equation very easily. In free electron model, you do not need to apply any potential. So, therefore, V can be put 0. So, now it becomes h cross square by twice m multiplied by this factor. This is nothing but differential operator equal to E psi. If you solve this equation, then you get everything with certain boundary conditions. So, that is much easier, right. So, that is what is basically important, and we will talk about this solution in the next lecture, but let me tell you few important aspects about how different kinds of physical phenomena was explained using this approach, like photoelectric effect. It was discovered, it was explained by Albert Einstein. It is nothing but what? If I put a photo h nu actually, h nu, and it will emit an electron. That is what happens from a metal. Okay. You can see here light is falling on metal and the electrons are ejected. So, therefore, how it happens? Very easily. Once electrons are bound to the atoms, if you put enough energy to break them away from the atoms, it will come out. That is what happens. So, you can see here this is potassium, it has minus 2 electron volts needed to eject an electron, because that is what the energy by which electrons are bonded with the nucleus. So, if you put 1.77, it will not come out, it will 2.25, it will come out at a very high velocity. If you 3.1 V, it will come at a much higher velocity. You can see the velocities are given here. So, therefore, that is what is photoelectric effect, and it can be easily explained using this quantum mechanics. This is one such thing which can be easily explained by quantum mechanics. So, let us stop here. We will talk about how to use this quantum mechanical techniques to explain the conduction very easily, but without not much solving of the complex equation. So, thank you for your attention. We will come back to the next lecture on more on this.